Heart rate, we said last time, is determined by the pace that is set in the SA node, right? There's a certain pace that's set in the SA node. Now, the SA node has an intrinsic firing rate of about 100 action potentials per minute, all right? And this number differs from the number we talked about before. If you remember a couple of classes ago, we said that the SA node fires 70 action potentials per minute. This number is different because this is the SA node outside of the body, right? If you had an SA node intrinsically, if you had it in a lab, right, it was not in your body, it could fire 100 action potentials per minute, okay? But when we do have the SA nodal cells inside the body, they are influenced by the autonomic nervous system. Which division of the nervous system did we say slightly predominates? Which? The parasympathetic, right? So at rest, both divisions of the nervous system are active and the parasympathetic slightly predominates. As a result, that is going to bring that firing rate from 100 action potentials down to 75 action potentials per minute, okay? All right, so the parasympathetic system is basically holding down the SA nodal cells so that they're not firing at that 100 action potential per minute, okay? In instances where we need to increase the heart rate, we could do so. If you're in the fight or flight mode, if you're running, if you're trying to escape some sort of danger, your heart rate can go up, right? It does go up, okay? The heart rate can go up to about 180 beats per minute, which is very fast. All right, in fact, athletes have, babies have a higher heart rate. Their rate is about 100 beats per minute. Athletes have a lower resting heart rate. Their rate is about 50 beats per minute. But the normal resting individual has a heart rate of about 70 to 75 beats per minute. All right. Okay, so let's talk about the sequence of events by which we can increase the heart rate, right? We can increase the heart rate. And this is going to be, again, a revision of a lot of things we already talked about. So what receptor is found in the heart? What adrenergic receptor? Beta 1, right? So beta 1 receptors are the adrenergic receptors that we talked about that are found in the heart. So let's say you're trying to get away from some type of danger. There's lots of epinephrine and norepinephrine flooding your system. They're gonna bind to those beta 1 receptors, and these receptors are in the SA node, right? And this is going to increase the opening of sodium channels and calcium channels, right? Do you remember that action potential sequence of events that we drew the other day, right, in the pacemaker cell? What was causing the initial depolarization? What channels? What was the channel that we said open? What did I call those channels? Funny channels, right? So the opening of those funny channels was what caused the initial depolarization of these pacemaker cells, right? We also talked about the opening of slow or T-type calcium channels, which cause that slow depolarization. So the influence of the beta receptors on these two channels is what can increase the depolarization of the cell and therefore increase the heart rate. Okay, so these cells are going to make it easier for an action potential to be fired. They're going to stimulate the cell, all right, and increase the rate at which they spontaneously depolarize, and that as an effect is going to increase the heart rate. So let's look at this sequence of events here. Now, this entire cascade should be a review for you. All right, we talked about norepinephrine binding to a beta 1 receptor, right? That was coupled to a stimulatory G protein because it was metabotropic. All right, that is going to influence adenylate cyclase to be increased, which is going to increase the production of cyclic AMP. And then we said cyclic AMP is going to enter the cell and turn on protein kinase. And that's where we sort of stopped when we looked at that cascade last time, right? So what does that protein kinase then do that actually speeds up the heart rate? So protein kinase is going to augment or increase the opening of those funny channels, which is going to help the cell depolarize much quicker. All right, so it's going to open up these funny channels, more sodium can rush in, and we're going to depolarize that cell even easier. As a result, we're going to fire lots of action potentials, and we're going to speed up the heart rate. Okay? We're also going to open those slow calcium channels, right? Those T-type channels. And that is going to also influence the cell to depolarize much quicker, which is going to speed up the heart rate. Right? So these two channels, or the augmentation of these two channels, happen by that protein kinase, and that is a sequence of events by which norepinephrine binding to this receptor increases the heart rate. All right, let's talk about the parasympathetic side, right? The parasympathetic side. Now, in the parasympathetic side, we had the activity of your vagus nerve. And what was the neurotransmitter that the postganglionic parasympathetic neurons released? What was that neurotransmitter? Acetylcholine, perfect, acetylcholine. So the acetylcholine that's released from that postganglionic neuron, which is a part of your vagus nerve, is going to bind to a muscarinic cholinergic receptor. All right, just to refresh you here, we talked about two types of cholinergic receptors, your muscarinic, your nicotinic, right? We said nicotinic was in skeletal muscle. It was also at the autonomic ganglia, so it was located on the postganglionic neuron. But we said on the effector tissue, there was muscarinic receptors, right? So on your cardiac SA node is a muscarinic receptor. Acetylcholine binds here, and that is going to increase the open state of your potassium channels and the closed state of your calcium channels. All right, and this is going to make it hard for the cell to depolarize. This is going to prematurely force the cell into repolarizing. If we open potassium channels and close calcium channels, what are we doing? What are we doing there? What did we say we're doing? That final phase of the sequence of events. We're repolarizing the cell, right? We're repolarizing the cell. We're kicking potassium out and we're stopping the influx of calcium. So having this effect in the cell is going to make it hard for the cell to be depolarized. It's going to force the cell into being repolarized, which is going to slow down or delay or decrease the heart rate. All right, let's look at the sequence of events. So we have acetylcholine, right? Acetylcholine. This is at the neuroeffector junction, right? Make sure you're tying all of these concepts together. You have acetylcholine. It's going to leave a varicosity. It's going to diffuse across that membrane. It's going to bind onto your muscarinic cholinergic receptor. All right, that is a metabotropic receptor, and so it is coupled to a G protein. That protein is going to have a change in its shape, and it is going to influence two other channels on the membrane here. The first one is your T-type or your slow calcium channel, and it's going to close those channels. It's going to close those channels. And if you close that calcium channel, we can't get calcium coming into the cell. It's going to be hard to depolarize this cell. All right? The second effect is that it's going to open up potassium channels. All right? It's going to open up potassium channels. What was the first step of the initial depolarization of a pacemaker cell? What was the first step there? We had to close the calcium channel, the potassium channel, right? We had to close the potassium channel, right? So that potassium would stop leaking out of the cell. This is needed to help the cell depolarize. If we force these channels open, potassium just leaks out of the cell and it's almost impossible to depolarize the cell. Okay, and that is the effect of acetylcholine binding onto this muscarinic receptor. It's going to inhibit or delay or prevent this pacemaker cell from depolarizing, which will eventually slow down the heart rate, okay? All right, so let's take a look at this graph, which shows the influence of the sympathetic system, the parasympathetic system. So our curve here in blue is the parasympathetic influence. Now again, this curve should look very familiar to you. This is your initial depolarization, your slow depolarization, your rapid depolarization, and then your repolarization. So this is an action potential in a pacemaker cell, okay? Now, the curve in blue is showing us that only one action potential is fired in this 1.4 seconds, right? Only one action potential can be fired. And that is under the influence of the parasympathetic system. So we're making it so hard to fire an action potential that we can only fire one in that 1.4 seconds. The curve in green is showing us the opposite. So the sympathetic influence is making it so easy to depolarize that pacemaker cell. It's so easy to fire an action potential that we can fire 3 action potentials in that 1.4 seconds. All right, so in that time, that same amount of time, under the sympathetic influence, we can fire 3 action potentials. Under the parasympathetic influence, we can only fire 1 action potential. All right, and what's happening at rest? So at rest, which is the curve in gray, there's an equal influence of both of these divisions. So we have sympathetic and parasympathetic, with parasympathetic being a little bit more dominant. Right? And this is slowing down the heart rate, but also not slowing it to where parasympathetic dominates. And this gives us a nice in-between number, which is 2 action potentials in that 1.4 seconds. Okay, so the influence of sympathetic and parasympathetic on the pacemaker cells is what keeps the heart rate at a nice in-between steady resting rate, which happens to be 70 to 75 action potentials per minute. So this is in a single pacemaker cell. I don't know if I'm understanding your question. Could you repeat it again? Yep. So in everyone's SA node, you have action potentials being fired, right? And again, depending on if you're an athlete, if you're muscular, if you're sedentary, if you are living in a cold climate, actually, higher altitudes, this is going to change. It's also going to change throughout the day. When you wake up in the morning, your heart rate is a little bit lower. At the end of the day, it's a little bit higher. But the overall picture here is that both influences of the autonomic nervous system is what keeps your heart rate in the middle. If sympathetic dominates, we're going to increase heart rate. If parasympathetic dominates, we're going to decrease heart rate, okay? All right, now there's also a few hormones that have an effect on the heart rate as well. There's epinephrine, and epinephrine is going to mimic the response of the neurotransmitter norepinephrine. All right, so you're gonna have that same sequence of events when epinephrine binds to a beta-1 receptor, as you did if norepinephrine were to bind. So norepinephrine as the neurotransmitter and epinephrine as the hormone have the same effect in the cell, and both of them can bind to a beta-1 receptor. Glucagon, on the other hand, is another hormone that circulates throughout your body, and this is going to increase your heart